From today, we are going to start quantum statistics. As you know, quantum statistics is of two types. First one is known as Bose-Einstein statistics, and the second one is called Fermi-Dirac statistics. Actually, we will learn about these two quantum statistics one by one. So first of all, we are going to start today uh, the Bose-Einstein statistics. And the basic principle of this Bose-Einstein statistics is based on a particular distribution function which is called Bose-Einstein distribution function. So in this lecture you will see what is this Bose-Einstein distribution function. Actually some people also say this as a Bose-Einstein distribution law. So definitely this is the basic theory of Bose-Einstein statistics, because all the applications based on this Bose-Einstein statistics will need the expression for the Bose-Einstein distribution function. So this is actually very important lecture, because this is the basic lecture on Bose-Einstein statistics. So first of all, we will see what type of particles obey this Bose-Einstein statistics. Okay. As you know, since Bose-Einstein statistics is a quantum statistics, so it is obvious that in case of quantum statistics, you have already studied earlier that the particles under consideration which will obey Bose-Einstein statistics must be identical and indistinguishable. This is a remarkable fact, that in quantum statistics particles are not distinguishable but indistinguishable. Okay, it means whenever we consider a quantum system, the wave packets of the particles get overlapped and the distinguishability of particles disappear, and we simply say that the particles are indistinguishable. Okay. Again, as you know, in quantum mechanics, a spin of the particle plays a vital role. So here, a spin of the particle will be also taken under account. In fact, Bose-Einstein statistics is obeyed by those particles which have integral spins. As you know that this spin of particle is measured in the units of h bar. When you say spin, that means a spin angular momentum, and this spin is actually integral multiple of h bar. So in units of h bar, you can say that the particles having 0 spin or spin h bar or 2h bar or 3h bar and so on. If the particles have spins like this, then those particles will obey the Bose-Einstein statistics. Okay, so definitely these particles must have a spin either 0 or h bar or 2h bar or 3h bar. You know, h bar is h divided by 2 pi. Okay. In fact, the particles having these integral spins have wave functions which are symmetric. It means only those particles will obey Bose-Einstein statistics which have symmetric wave function. When you say symmetric wave function, what does it mean? If you consider that there is a system of two particles, and in a particular quantum state the wave function is psi of 1 2, then after the interchange of the spin and position coordinates, or you can say also that after the exchange of particles, if the wave function is psi of 2 1, and psi of 1 2 is equal to psi of 2 1, then you simply say that the wave functions are symmetric. So definitely the particles obeying this Bose-Einstein statistics, which is actually called in brief BE statistics, wherever I have written BE, that means Bose-Einstein. Okay. So these particles obeying BE statistics must have symmetric wave function. It means psi of 1 2 must be equal to psi of 2 1. Okay. And you know that any particle which has symmetric wave function, that particle does not obey Pauli's exclusion principle. You have already studied these things in quantum mechanics. If you have not studied, go through my channel and you will find a very detailed explanation of a spin angular momentum in the playlist of quantum mechanics of my channel. Okay. So in quantum mechanics we study that the particles having symmetric wave function do not obey Pauli's exclusion principle. You know what is this Pauli's exclusion principle? Pauli's exclusion principle simply states that the particles having the half integral spin, only one such particle can remain in a particular quantum state. But if the particle has integral spin, there is no restriction on the number of particles occupying a particular quantum state. It means in a given quantum state, any number of particles having integral spin can remain. Okay. So these particles which obey the Bose-Einstein statistics do not obey Pauli's exclusion principle. Okay. So these are the basic properties of the particles that will obey Bose-Einstein statistics. Okay. In fact, these group of particles which have these properties which I have just mentioned, or in brief you can say the particles which obey the Bose-Einstein statistics, are collectively known as bosons. Okay. In fact, Bose is a famous Indian scientist, Satyen Bose, and on the name of Satyen Bose, these particles are called bosons. Actually, idea of this Bose-Einstein statistics was proposed by, in fact, Satyen Bose, which was a great Indian scientist, famous Indian scientist. Okay. While studying the black body radiation, or he was trying to derive Planck's law, and in fact in dealing with that problem, he proposed this Bose-Einstein statistics. Okay. So the particles which obey Bose-Einstein statistics are collectively known as bosons. Some of the important examples I have mentioned here of these bosons, these are photon, phonon, pi meson, God particle, which is also called Higgs boson, and all nuclei with even mass number. All nuclei with even mass number are actually bosons. For example, if you take He4, which is also called alpha particle, as its mass number is 4, that is, it is an even number, so definitely this nucleus will be a boson. Okay. So I hope you have understand what are the basic feature or what are the basic property of the particles called bosons which will obey Bose-Einstein statistics. Okay. As I have told you that this Bose-Einstein statistics is framed is based on a particular function which is called Bose-Einstein distribution function, or that is also called Bose-Einstein distribution law. So first of all, we will discuss in this lecture what is this Bose-Einstein distribution function or Bose-Einstein distribution law. And after that, in the forthcoming lecture, we will see the application part of this Bose-Einstein statistics. So let us start to know about the Bose-Einstein distribution function. This BE stands for Bose-Einstein. See here, the page has been turned, but this will be just okay, don't worry. So see, this Bose-Einstein distribution function, or you may also call it Bose-Einstein distribution law. Okay, actually, to know what is this Bose-Einstein distribution function, just you have discussed the Maxwell-Boltzmann distribution function. On the same line, here we will discuss this problem. Okay, only the manner of distribution will be different because the particles are in fact in this case indistinguishable. Okay, and for this, let us consider there is a system of bosons enclosed in, let us consider a enclosure containing enclosing volume V, and the total number of particles, that is bosons, inside this enclosure is N, and its temperature is T. Actually, at this temperature, this bosonic system is in thermal equilibrium, you can say. In fact, all these N bosons, okay, have the same Hamiltonian, or you can say that all these particle finds itself in the Hamiltonian, let us say H. And this Hamiltonian H has the energy eigenvalues given by E1, E2, E3, and so on. You can also write the last value, this is En. Actually, N represents the number of energy eigenvalue, or the energy levels, you can say. Okay. In fact, each of these energy eigenvalues or energy levels, you can also say, are degenerate. Okay. It means there will be more than one quantum state corresponding to any energy eigenvalue. And for this, let us consider that the ith energy level or the ith energy eigenvalue EI is GI fold degenerate. GI is the degeneracy of this ith energy level or this ith energy eigenvalue EI. When you say that this EI has EI is GI fold degenerate, or the degeneracy of this energy eigenvalue EI is GI, what does it mean? It means there will be GI quantum states corresponding to this energy eigenvalue. And as you know, the eigenstate is represented by the eigenvector. Okay, so it means this EI energy corresponding to this EI energy eigenvalue, there will be GI eigenvectors. Normally, these eigenvectors are denoted like this. This is ket phi I1, ket phi I2, and so on, ket phi I GI. These are the eigenvectors representing the eigenstate or the quantum state. Okay, so in simple manner, you can say that this EI energy eigenvalue is GI fold degenerate, or its degeneracy is GI. It means in this energy level there are GI quantum states, and these quantum states are represented by these eigenvectors ket phi I1, ket phi I2, and so on, ket phi I GI. Okay. Now let us consider a particular configuration of our system containing the total number of particles N. Let us form a configuration which I have mentioned it here. You can see. Consider that N1 represents the number of particles, that is number of bosons, in which each particle has energy E1. Okay? And this energy eigenvalue, which is energy eigenvalue of each of N1 particle, is G1 fold degenerate. It means in this energy level there are G1 quantum states. Okay? Similarly, N2 is the number of particles each with energy E2, and this energy eigenvalue is G2 fold degenerate. It means the number of quantum states in which all these N2 particles will be distributed is equal to G2. And similarly, you can say that in these Ni are the number of bosons each with energy eigenvalue Ei, and the degeneracy of this energy eigenvalue is Gi. Okay? And finally, the nth in nth energy level there are Nn particles, and this energy level is Gn fold degenerate. Okay? Now, the basic problem to know the distribution function is how we can distribute these particles among the different quantum states. It means our prime aim is to find the number of ways in which these N1 particles can be distributed in G1 quantum state, N2 particle can be distributed in G2 quantum state, and so on. So let us try to find in how many ways these Ni particles in general with each energy Ei can be distributed in Gi quantum state. How we can find this number? Let us try to know it. And for this, we consider here this array. You can see this figure. Actually, in this figure, this vertical, each of these vertical line, let us consider, represents the quantum state. Vertical line represents quantum state. These vertical lines are QS, quantum state. Okay? And these dots which I have made in the right side of a vertical line, actually that dot represents the number of particles in that quantum state. Okay? So you can say that the line represents the quantum state, and the dots in the right side of the line represent the quantum represent the particles contained in that quantum state. Okay? Now, as you know, just we have learned that these bosons do not obey the Pauli exclusion principle. When you say that these do not obey the Pauli exclusion principle, what does it mean? It means there is no restriction on the number of bosons found in a particular quantum state. It means in any quantum state, any number of bosons can remain. Actually, further we will learn in the forthcoming lecture that actually these bosons have a tendency of grouping. These particles tend to occupy the same quantum state. Okay? So, keeping this fact in our mind, now we will try to find the number of ways in which these Ni bosons can be distributed in Gi quantum state. How many ways there will be of distribution. Okay? And for this, let us consider this first line, which represents actually the first quantum state. We consider that this line is fixed. Okay? So, Excluding this quantum state, the remaining number of quantum states will be what? Since the total number of quantum states here is Gi, and you have taken this particular state fixed, so remaining number will be Gi minus 1. This is the remaining number of quantum states. Okay, and there are Ni particles. So in this array there are how many total objects? Objects means this quantum state and the number of particles, these are treated like object. So you can say that the total number of objects in this array will be Ni plus Gi minus 1. Okay, that is the number of particle plus number of quantum state, that will be Ni plus Gi minus 1. Okay, when we keep the first quantum state or first vertical line fixed, so I have mentioned it here, you can see that this Gi plus Ni minus 1 objects can be arranged in how many ways. So now the problem is how we can arrange these Gi plus Ni minus 1 object in these quantum states. Actually, as there is no restriction, Pauli's exclusion principle is not obeyed. So you have definitely learnt in the theory of permutation and combination that these Gi plus Ni minus 1 objects can be distributed among these Gi minus 1 quantum states by how many number, how many ways? Actually, this number of ways will be simply the permutation of this Gi plus Ni minus 1, which is simply the factorial Gi plus Ni minus 1. Okay, Gi plus Ni minus 1. So you can see I have mentioned it here that in this array there are Gi plus Ni objects, and keeping the first quantum state, that is the first line fixed in its place, the remaining Gi plus Ni minus 1 objects can be arranged in Gi plus Ni minus 1 factorial independent ways. Okay, but in fact here actually there are two meaningless permutations too. Two meaningless permutations. In fact, when you permute the quantum states which is Gi minus 1 among themselves, that number will be Gi minus 1 factorial. But permuting the quantum state among themselves actually do not create any independent or new state. So this permutation is actually a meaningless permutation, and definitely we have to subtract from this value Gi plus Ni minus 1 factorial this meaningless permutation. Okay, and apart from this meaningless permutation there is another meaningless permutation too. When you permute the particles among themselves, what is the number of particles? Ni. When Ni particles are permuted among themselves, then the number of ways will be Ni factorial, and this permutation also do not give any new state. So this is also a meaningless permutation. Okay, and therefore the actual number of ways in which these Ni particles can be distributed in Gi quantum states, that will be found simply by dividing this Gi plus Ni minus 1 factorial by the product of the factorial of Ni and Gi minus 1. because this is probability, so a subtraction means you have to divide. Okay, so you can say that thus the number of ways in which Ni particles can be distributed in Gi quantum states, or the number of microstates which are equally priori probable, is given by. What will be that number? As I have told you, this will be simply equal to Wi, and that is equal to what? That is equal to Gi plus Ni minus 1 factorial and divided by Ni factorial, this is first meaningless permutation, and times Gi minus 1 factorial. Okay. So this is the actual number of ways in which these Ni particles can be distributed in Gi quantum state. In the similar manner, you can say what will be the number of ways in which N1 particles can be distributed in G1 quantum state, N2 particle can be distributed in G2 quantum state. Okay. So the total number of ways of distributing the particles N1, N2, so on Nn in the n energy levels, what will be that number? Actually, that number W will be equal to W1 times W2 times W3 and so on. And this can be written as product of I1 to N Wi. Okay, product of Wi. So you can see I have written here that this total number of ways which is denoted by the symbol W is equal to product of Ni plus Gi minus 1 factorial and divided by Ni factorial times Gi minus 1 factorial. Okay, so this is actually the number of maximum number, you can say, of microstates corresponding to the most probable macrostate, or in other words you can say that this W is nothing, this is the maximum thermodynamical probability. Okay. Now after getting the value of this W, this expression you can compare is different from the value of W which we have obtained in the Maxwell-Boltzmann distribution law. But after this step, each and every step of calculation will be exactly same which you have learnt in the case of Maxwell-Boltzmann distribution law. So all the mathematical steps which we have followed in that case will be exactly same in this case too. Okay. So first of all, we will have to change this product into summation, and for this we must take the log of equation 1, natural log. Actually this, as I have told you while dealing with the Stirling formula, that calculation of factorial of any large number is very troublesome. And here Ni plus Gi minus 1 factorial, Ni factorial, Gi minus 1 factorial, all these are very large number. But when we take the logarithmic values of these numbers, then it is easier to find by using the Stirling formula. So definitely, first of all, we have to take the natural logarithm for simplicity. Okay. So after taking natural log of this equation 1, what will be your result? Actually, you know, when we will take the natural log, the sign of product pi will change into sign of summation sigma. Okay. And what will be your result? You can see this log W will be summation over I 1 to N. Okay. Times log Ni plus Gi minus 1 factorial minus log Ni factorial minus log gi minus 1 factorial. Okay, because log a by b you know is equal to log a minus log b. Okay, now each term inside this square bracket can be simplified by using the Stirling formula. You know that this Stirling approximation or formula is what? Ln n factorial is equal to n ln n minus n. Okay, so using this Stirling approximation or Stirling formula, we will actually see what will be these three terms inside the square bracket. Okay, so you can see this ln w can be written as summation over I1 to n, and the first term is log ni plus gi minus 1 factorial. So using a Stirling formula, what will be this? This will be ni plus gi minus 1 times log ni plus gi minus 1 minus ni plus gi minus 1. Okay, at the place of n you can see here there is ni plus gi minus 1, and log ni factorial, see here log ni factorial, this will be what? This will be ni log ni minus ni. Okay, and then there is minus log gi minus 1 factorial, so this will be minus gi minus 1 ln gi minus 1 minus gi minus 1. Actually, using this Stirling formula, I have simplified all these three terms. Okay, now see, we will simplify this result. This will be summation over I ni plus gi minus 1 log ni plus gi minus 1. This is at each. And here there is minus sign before this bracket. So after removing the bracket, what will be these terms? This will be minus ni minus gi and plus 1. Okay. Now here we also remove the bracket in this term. You can see this will be then minus ni log ni and minus minus plus. So this is plus ni. Okay. And the last term is minus gi minus 1 log gi minus 1 and minus gi minus 1. Okay, but since here is already minus sign before this, so this will be plus gi minus 1. Okay, plus gi minus 1. Now you can see this minus ni and this plus ni will cancel out. This minus gi and this plus gi will cancel out. This plus 1 and this minus 1 will cancel out. Okay. So the remaining terms are what? This is summation over I ni plus gi minus 1 times log ni plus gi minus 1 and minus ni log ni and minus gi minus 1 log gi minus 1. But as you know, in a statistical system, Ni is very large. This is number of particle. Okay, and so this Ni plus Gi will be much greater than 1. So we can neglect this 1 in the first term. Okay, so you can see after neglecting 1, what will be your result? I have mentioned here that actually 1 is much smaller than Ni plus Gi for any real statistical system. So we can neglect it. So after neglecting that 1, you can write ln w equal to summation over I Ni plus Gi log Ni plus Gi minus Ni log Ni minus Gi minus 1 log Gi minus 1. Okay. But as you know, this W is actually the maximum number of microstates or maximum thermodynamical probability. So this ln W will be also maximum. And if ln W is maximum, you know from calculus that differential of this ln W will be equal to 0. So now let us take the differential of this ln w, which has been defined here, which I am just taking, you can see, and that will be equal to 0. So after taking the differential of ln w, what will be your result? This is summation over I, and see, the first term is ni plus gi times log ni plus gi. So this is product of two functions. First one is ni plus gi and second is log ni plus gi. So we will follow the rules of differentiation of product of two functions. So take the first function ni plus gi at each and differential of log ni plus gi. What will be that? That will be 1 over ni plus gi times differential of ni plus gi. Ni plus gi. But this will be simply dni plus 0, that is dni, because gi is number of quantum state, and number of quantum state in a particular energy level is fixed, is constant. So dgi will be 0. So I have written here dni. Okay. Now we will take this second factor log ni plus gi at each, and we will take the differential of this ni plus gi. You know, the differential of ni plus gi will be simply dni, because dgi equal to 0. Okay. Now take the differential of this second term, that is minus ni log ni. Here there is also a product of two functions. One is ni and another is log ni. So what will be this? This will be minus ni and differential of log ni. This is 1 by ni into dni, and plus now log ni into dni. And as I have told you that this number of quantum states in a given energy level is constant, so the last term is a constant, and since it is a constant, so its differential will be 0. So I have written here 0, you can see, and that is equal to 0. Now let us simplify. This ni plus gi and ni plus gi will cancel out. Here this ni and this ni will cancel out. Okay. Now you can see this dni is present in all terms inside this square bracket. So you can take this dni just as a common factor. So after taking this as a common factor, what will be inside the square bracket? In first term you can see 1 will remain. In second term log ni plus gi will remain, and here this will be minus 1 and minus log ni. So you can write this expression like this. This is summation over I log gi ni plus gi plus 1 and minus 1 and minus log ni dni equal to 0. Now this 1 and this 1 will also cancel out. Okay. And the remaining terms are summation over I log ni plus gi minus log ni dni equal to 0. As you know that this log ni plus gi minus log ni will be what? This is log ni plus gi divided by ni, and this is equal to 0. Okay. Now after getting this result, we will again use the concept of Lagrange indeterminate multiplier. And for this we have to think that, as I have told you earlier, that the system under consideration, which is a bosonic system, is inside an enclosure and the number of particles n is constant, because this system is just an isolated system and it does not exchange either particle neither particle nor energy with the surrounding, and its total energy E is also constant. Okay. So taking this fact under account that the number of particles and the total energy are fixed, what will be your result? You can see. As the total number of particles can be written as n1 plus n2 plus so on plus nn, and that can be written in brief as summation over I ni. Summation over I ni. You can write. Okay. Sorry, the page is just turning. And this is equal to constant. Okay. And so the change in summation ni, that is summation over I dni, will be equal to 0. Again, what will be the total energy? As you know that n1 particle, in n1 particle each has energy E1. So total energy of n1 particle will be n1 into E1. Again, in n2 particle each has energy E2. So the total energy of n2 particle is n2 E2. And in this way you can find the energy of different group of particles, and after summing it you will get the total energy U, and this can be written as summation over I NiEi. So this summation over I NiEi, this represents the total energy of the system, and that is constant. So taking its change, what will be your result? This is summation over I Ei dni equal to 0. Now we will use the concept of Lagrange undetermined multiplier, and for that what we do, let us multiply this equation 3 by a parameter alpha and this equation 4 by another parameter beta. And after multiplying by alpha and beta, we will add these two equations in this equation number 2. And since after multiplication these two terms will remain 0, it will not change. Okay. So let us see what will be the result. See. So after adding these two equations after multiplication by alpha and beta, what will be your result? Summation over I log ni plus gi over ni plus alpha plus beta ei times dni equal to 0. Actually dni has been taken as a common factor. Okay. Now if we consider the particular value of alpha and beta, then definitely each term should be separately 0. It means dni you can take equal to 0 and this term inside the square bracket equal to 0. In other words, you can say since dni are independent variables, so for all values of dni this result will be 0 only when the term inside this square bracket is 0. So let us equate to 0 the term inside the square bracket. The term is what? This is ln ni plus gi over ni plus alpha plus beta ei equal to 0. And this can be written as ln ni plus gi over ni equal to minus alpha plus beta ei. Okay. And so that ni plus gi over ni will be what? This will be exponential minus alpha plus beta ei. Okay. And now divide these ni plus gi by ni separately, and this will be 1 ni by ni plus gi over ni, and that will be equal to exponential minus alpha exponential minus beta ei. Okay. Now take this one in RHS. So this will be gi over ni, and that is equal to exponential minus alpha exponential minus beta ei minus 1. And so that ni by gi will be what? This will be 1 over, you can see here, 1 over exponential e to the power minus alpha and exponential e to the power minus beta ei minus 1. Okay. But you have learnt in Maxwell-Boltzmann distribution law, what is this Ni by Gi? What is this? Actually, we have denoted this by the symbol f of Ei earlier. Here we will again denote this quantity by f of Ei. But what is this? You know, this is called occupation probability. This Ni by Gi, which is denoted by the symbol f of Ei. What is this? This is called occupation probability. And what is this occupation probability? You can see Gi is the number of quantum state and Ni is the number of particles distributed among those quantum states. So you can say that in Gi quantum states, the number of particles present is Ni. So in one quantum state, what will be the average number of particles? That will be Ni over Gi. So what is this Ni over Gi? This is average number of particles. Here you can say average number of bosons in one quantum state, yeah, per quantum state. And the average number of particles per quantum state is called occupation probability, or it is also called distribution function. Okay. So you can see I have written here that this f of Ei is equal to 1 over exponential minus alpha exponential Ei by kt minus 1. Actually, you know that this beta is equal to minus 1 over kt, where k is Boltzmann constant. Okay. So instead of beta, I have written actually minus 1 by kt, and so this will be e to the power Ei by kt. Okay. In fact, we will learn after this lecture that this parameter alpha is related to the chemical potential of this system. So if mu is the chemical potential, then it turns out that alpha is equal to mu over kt. Alpha equal to mu by kt. So instead of alpha in this above expression, you can write mu by kt. Okay. Now, if we consider that the energy eigenvalues are almost continuous, not discrete, in that condition, we simply drop the subscript I, and this f of Ei is simply written as f of E. Okay. So dropping the subscript I, you can write this expression here in this manner. This is 1 over exponential E minus mu by kt. See here, Ei will be now E and alpha is equal to mu by kt. So this can be written as E to the power E minus mu by kt and minus 1. This function f of E, this is actually called the distribution function. But we have obtained this distribution function on the basis of Bose-Einstein statistics, or on the basis of statistics which obeys Bose-Einstein statistics. So this particular function is also called Bose-Einstein distribution function. Okay, that is BE distribution function. Okay, and this equation is also known as Bose-Einstein distribution law. This is also called. Okay. So this is the expression for the Bose-Einstein distribution function. Actually, we will discuss this Bose-Einstein distribution function after some lectures. Here our aim was only to derive this result. But as I have told you earlier, whenever you will discuss any theory based on this Bose-Einstein statistics, the basic equation which will be used to explain that phenomenon will be this distribution function. So you must remember the expression for this Bose-Einstein distribution function for the clear-cut understanding of the forthcoming lectures. Okay, so I hope you have definitely enjoyed this video, and so if you have enjoyed, you must write these things in your notebook, as I have told you several times that that will be a very good notes if you are preparing for civil services examination or any state public service commission examination, taking physics as an optional subject. This type of discussion, this type of question is very important for you. Okay, thank you very much.